Good morning. So, chemistry second year, English medium. Our chapter is D and F block elements and coordination compounds. Our topic is transition elements. Okay. So, in the previous class, we discussed how the D block elements are existed in the periodic table and their position, then physical properties, especially here is melting points, boiling points. Then, so these are discussed. Then the continuation of the topic is what? It's atomic and ionic sizes of transition elements. Okay, in the physical properties, atomic and ionic sizes of transition elements we will discuss today. Yes. So when you observe here is a D block elements, especially here is a transition elements, they are in 4 series, 3D series, 4D series, 5D series and 6D series. Then in which first 3D series, 4D series and 5D series chemistry is here. Then yes, so when you observe the transition elements, atomic and ionic sizes is here is a scandium. When you observe the scandium size, here is a scandium size is somewhat greater. So when compared with here is a titanium, vanadium. Then yes, while increasing here is a atomic number is from left to right in the periodic table. Then gradually the size of the atoms decreased. Then after that here is after nickel somewhat here is size of the zinc is somewhat greater. The reason is what? Then while increasing the atomic number here, yes, here is because of the lot of electronic repulsions in the atom, yes, electron cloud can be expanded. That's why here is zinc size is somewhat greater than the copper. Okay, then next one is the remaining elements: yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, and then next one is a 5D series elements. These graph trends express the size of the 4D and 5D series elements. Then when compare with this one is the first 3D series elements, then it's here is what? The 4D and 5D series elements sizes are somewhat closer. That is, the size of the 4D and 5D series elements is somewhat closer. So this is the based on this graph. Then what happened? Yes, then same is from scandium to yttrium, yttrium to lanthanum. While increasing the atomic number, size will be increased. So this is same in group property. Scandium to lanthanum is the atomic sizes are increased while increasing the atomic number. Whereas in titanium, zirconium and hafnium, then is okay, is a titanium size is somewhat here is smaller when compared with zinc, but here is a zirconium. Then zirconium and hafnium atomic sizes are, yes, here is their sizes are almost similar. Reason is what? Suppose when observe the zirconium atomic size, there is a 1.6 angstroms, then are 160 picometers. Then zirconium size is 1.6 angstroms or 160 picometers. Then whereas here is a hafnium, that is 1.59 angstroms or 159 picometers. 159 picometers. Then that means is a hafnium size is smaller than here is a zirconium. So what happens is what? Then yes, here is after there is a lanthanum. So 57 is lanthanum, then 72 is hafnium. In between 57 and 72 here is there is lanthanides, cerium to lutetium elements. That means then yes, here is after lanthanum the 58 electron not enters in n-1 d orbitals. Okay, then this differentiating electron enters here is a 4f orbitals. That's why here is after completion, after filling of 4f orbital, then the 72 electron enters into the, yes, here is what is a dn-1 d orbitals. That's why is a zirconium and hafnium are having, yes, almost similar atomic sizes. So this is because of lanthanide contraction. After lanthanum, 58th electron not enters the n-1 d orbitals. That electron enters 4f orbitals. 4f orbitals. That's why here is what then next one, yes, a total completion of the 4f orbitals. Then next one, the 72 electron enters into n-1 d orbital. That is, here is hafnium. That is in between lanthanum and hafnium. Here is 14 elements are here. Then a lanthanide contraction is happened. Lanthanide contraction is happened. So because of the lanthanide contraction, that effect influence the size of hafnium. That's why its size is also smaller. So what is meant by lanthanide contraction is, in lanthanide contraction, then is in general, is a differentiating electron enters into, here is a n-2 f orbitals. Then while increasing the atomic number, then atomic size of the elements are gradually decreased. Then, so due to this reason, so this, because of lanthanide contraction, here is a hafnium is also having smaller size. It's a lanthanide contraction influence decides the size of a hafnium. That's why here is almost, then is a 5D series elements. 5D series elements sizes are similar with 4D series elements sizes. That's why these lines trends in is atomic radii of transition elements 4D and 5D somewhat closer. Okay, so this is the effect of lanthanide contraction. Okay, then next one. Then when you take the, again here is a zinc, cadmium, mercury, in the same way, yes, when compare with the copper, silver, rhodium, their sizes are larger. Again the reason is what? Then yes, here is because of the high repulsions among the electrons in the atom, electron cloud can be expand, their size is larger, though they are end of the here is a series. Okay, so this is about atomic and ionic sizes of transition elements, 3D, 4D and 5D series elements. Okay, then next one is, there is a ionization energies. What is meant by ionization energy? There is a ionization energy means what? Then is here is in order to remove a electron from the atom which is in gaseous state, here is how much of energy is required. That energy is called as ionization energy. Then yes, here is what from scandium to zinc, then yttrium to cadmium, then lanthanum to mercury. In the period the same from left to right. Then yes, while increasing the atomic number, so because of the size of the elements are decreased, then their ionization energies are very high. Okay, ionization energies are high. Then so this is because of smaller sizes. Then scandium to zinc, then yttrium to cadmium, then lanthanum to, here is a mercury. Okay, then this is about ionization energies. Then next one, here is a oxidation states. What is meant by here is a oxidation states. Then so oxidation states are the specific properties of the transition elements. Okay, then so transition elements exhibit variable oxidation states. This is the specific property. Okay, then so here is a scandium. Yes, next one, here is a yttrium, here is a lanthanum. So they do not exhibit the variable oxidation states. Remaining elements, titanium to, again here is a zinc, cadmium, mercury. Here is a zinc, cadmium, mercury also. Here is a zinc. In general, it exhibits the +2 oxidation state. Then here is what cadmium exhibits the +2 oxidation state. Then so here is a Hg, mercury exhibits the, here is a +1 and a +2. Then the remaining elements, scandium, yttrium, lanthanum, they do not exhibit variable oxidation states. Remaining elements exhibit variable more than one oxidation state. More than one oxidation state. Then it is a titanium +2, +3, +4. Then it is a vanadium, it is a +2, +3, +4, +5. Then chromium exhibits, here is a +2, +3, +4, +5, +6. It also exhibits +1, but that is very unstable. Then here is a manganese +2, +3, +4, +5, +6 and a +7 oxidation states. Then iron exhibits +2, +3, +4 and a +6. Then cobalt +2, +3, +4, nickel +2, +3, +4, copper +1 and +2. Then there is a zinc exhibits +2 oxidation state. Then yes, what is the reason behind the variable oxidation states of transition elements? Then already we discussed the electron configuration. Is a scandium. Here is a scandium, here is a 21, that is a 3d1, here is a 4s2, 3d1, 4s2, that is a 3 electrons. 3 electrons are removed. What happens? It exhibits +3 oxidation state. +3 oxidation state. As a result, it is getting a inert gas electron configuration, that is argon. Then that is s electrons and d electrons when they are involved in the chemical reactions. Okay, then the specific property of transition elements is, in transition elements, outer orbit electrons, ns electrons and penultimate shell n-1d electrons, both are involved in chemical reactions, are involved in bond formation. That's why they exhibit variable oxidation states. Suppose when you take the titanium, it is a titanium exhibits +2 only when s electrons involved in chemical reactions. Then +3, +4, then this is happened not only here is a s electrons and n-1d electrons also involved in chemical reactions, then it exhibits +2, +3, +4 oxidation states. But here is a +4 is very common oxidation state and a stable oxidation state. Okay, titanium in +4 oxidation state, it is stable oxidation state. Okay, then next one, here is a +2. At this stage it acts as a reducing character. Okay, so titanium in +2 oxidation state, it is reducing character. Okay, then next one, when you take the, here is a vanadium, here is a what? Here is a +2, +3, +4 and a +5. Then this +5 is very common oxidation state of vanadium. +5 is the very common oxidation state of vanadium. Then when it is exhibited +5, then is a titanium, here is a d electrons and s electrons, both are involved in chemical reactions, then is a +5 oxidation state is possible. Then vanadium, this is what 23 means what? 3d3 4s2. Okay, it's a d electrons 3, s electrons 2, both are involved in chemical reactions, then +5 oxidation state is happened. Okay, then next one is a chromium, then it exhibits, there is a +2 too, not only here is a +2, here is a +1 is also exhibited by chromium, but a chromium +1 oxidation state is very unstable. Then there is a +2 to +6 oxidation states are very common. Then here is a +6 is a very common, +6 and +3 are very common oxidation states in case of chromium. Then here is a manganese. There is a manganese exhibits, there is a +2 to +7 in 3D series. Then manganese exhibits highest oxidation states. Okay, then +2 to +7. In +2 is +2 and +7. Then +2 is what? In +2 state, what? Only s electrons involved in chemical reactions. Okay, then 3d5 half filled electron configuration, then it is stable electron, half filled electron configuration, it causes more stable. Then next one, here is what? +3 oxidation state. At this stage it act as, here is a oxidizing agent, oxidizing Mn +3 state, manganese act as oxidizing agent. Okay, then there is a +7. There is in +7 oxidation state, highest oxidation state of manganese in this. There is a series. Then next one, here is a iron exhibits +2, +3, +4, then here is a +6. Then +2 and +3 are very common oxidation states of iron. Then next one, cobalt +2, +3, +4 is a +2, +3 are common oxidation states. Then is a nickel +2, +3 and +4 is a +2 is very common oxidation state. Then next one, copper +1 and +2, then +2 is a stable oxidation state. Then here is a +1 is unstable. Then zinc is a only exhibits here is a +2 oxidation state, +2 oxidation state. Then d electrons not involved in here is a chemical reactions, only s electrons. Okay, then yes, when you observe the variable oxidation states of transition elements, here we are discussing only here is what then 3D series elements only. Then so when you take the there is a 4D and 5D series, and again here is what then so this is the sixth group. Then here is a chromium, molybdenum, then wolfram. Is a chromium +6 oxidation state is here is a unstable. Then next one is a molybdenum and wolfram. Molybdenum and wolfram +6 oxidation states are very stable oxidation states. Here is a chromium exhibits +3 is a stable. Then next one is here is what +6 somewhat unstable. Then molybdenum and wolfram is a stable +6 oxidation states. Then next one, so when you take the here is a manganese, then in manganese then is a +2. In +2 state D5 half filled electron configuration, it is a stable. Then is a when scandium to zinc, the +3 oxidation state stability will be decreased, that is +2 stability is increased. Then here is a zinc +2 oxidation state is a stable oxidation, stable electron configuration. In +2 state, yes, it is getting a 3d10 electron configuration, that is from left to right. Then +3 oxidation state stability will be decreased, +2 stability will be increased. Then next one, another thing of oxidation states is then so when you take the there is a lower oxidation states of metal ions, lower oxidation states of metal ions, they yes forms the ionic compounds, they forms the ionic compounds. Then yes, in higher oxidation states, then as a metal transition metal ions can form the covalent compounds. Next one is in +2 state, then so their compounds are considered as us compounds. Suppose here is a Fe +2, in +2 state, then iron forms the here is a ferrous hydroxide, then us compounds. Then in +3 state, then here is what higher oxidation states, they can be considered as eke compounds. Us compounds are very common in lower oxidation states, eke compounds are common in higher oxidation states. Then next one, here is a lower oxidation states, suppose here is a titanium, vanadium, here is a chromium, next one manganese, iron. Then in +2 oxidation states, what? Then lower oxidation states, they act as reducing agents. They act as reducing agents. Then whereas in higher oxidation states, then they act as here is a oxidizing agents. Chromium, so in +2 oxidation state, then it act as a reducing agent. Then in +6 oxidation state, then chromium compounds are here is what act as oxidizing agents. Okay? Then in lower oxidation states, yes, transition metal compounds act as reducing agents, higher oxidation states, they act as oxidizing agents. Then next one, suppose here is a copper, +1 compounds are very unstable, that is they involved in disproportionation reaction. +1 compounds, yes, +1 compounds, copper +1 compounds are very unstable, it involved in disproportionation reaction. So disproportionation reaction means what? There is a copper in +1 oxidation state, then it forms the, here is what, then Cu and Cu plus 2, that is copper ion undergoes oxidation as well as reduction. Okay, oxidation as well as reduction both are taking place in one ion, then that is called as, here is a disproportionation reaction. Then here is a copper plus 1, then from here to here what, oxidation takes place here. Oxidation takes place here, that is increase in oxidation number, electron is released. Then so this released electron gain Cu plus ion, then it is getting a Cu 0, copper 0. From here to here what, decrease in oxidation number takes place, this is called as reduction, this is called as oxidation. Then yes, within the same element here is a oxidation as well as reduction, both are taking place, that's why this is called as disproportionation reaction. In copper plus 1 compounds involved in disproportionation reaction. Then next one, here is a plus 2 compounds are very stable compounds, then especially here is what, in aqueous solutions Cu plus compounds are more stable, Cu plus compounds are more stable. Okay, then so this is about oxidation states. Oxidation, why transition elements exhibit variable oxidation states? Ns electrons and n-1d electrons both are involved in the formation of bonding, or both are involved in chemical reactions, that's why they exhibit more than one oxidation states. So this is the reason of variable oxidation states of transition elements. Then so let us see the, here is the electrode potentials and chemical reactivity. Then this is E naught is standard reduction potential. Okay, standard reduction potential values from, here is a M plus to M values increases, M plus 2 to M values increases, that is suppose here is what, here is a M, suppose you take the, here is a Mn plus 2, manganese plus 2 to, here is a 0, then values increases from, then here is a from left to right in the periodic table, that is what, especially in case of transition elements. The reason is what, here is IP values, ionization potential values. Ionization potential values are increased, that's why their standard reduction potential E naught values are increased. Then except here is a zinc. Zinc is having, then standard reduction potential value is a negative signs. Okay, negative sign, and a very lower, here is what, reduction potential values. Okay, then here is suppose because there is a E naught values, suppose you take the, here is a copper, here is a copper is having the positive value. Positive is a standard reduction potential value, that is a 0 plus 0.34 volts. Okay, so because of this reason, then copper cannot liberate the hydrogen gas from the aqueous solutions, especially aqueous acids, mineral acids. Okay, suppose when you take the, here is a copper when treated with HCl, then it cannot liberate the hydrogen gas from the HCl solution. The reason is what, its standard reduction potential value is in positive signs, that is plus 0.34 volts. Only the copper can interact with yes, especially here is HNO3 and H2SO4, oxidizing behavior acids, HNO3 and H2SO4, it can interact, but it cannot interact with the HCl. It cannot liberate the hydrogen gas. Okay, whereas remaining when you take the, here is a zinc, when zinc interacts with the HCl, then simply it can liberate the hydrogen gas from HCl. This is happened by means of, here is its standard reduction potential value is very less, that is in negative sign. Then so when you take the, here is a manganese, nickel, zinc have more negative standard reduction potential values than the expected values. Reason for this is why this is a manganese and zinc are having, yes, negative standard reduction potential values, then the expected reason is then in Mn plus 2 state it is getting, then manganese is what, it is 25 in plus 2 state, then only s electrons involved, then d5 configuration is happened, whereas here is in zinc, yes, again here is a d10 electron configuration. Because of more stable d5 and d10 electron configuration, their standard reduction potential values are very, yes, there is a more in, yes, especially negative standard reduction potential values, okay, more negative standard reduction potential values, then because of the d5 and d10 configuration. Yes, nickel is also having a then more negative standard reduction potential value, so because of the, yes, what, hydration enthalpies, because of the high hydration enthalpies, its here is a standard reduction potential value is negative sign. Then next one, suppose here is again here is a E0 standard reduction potential value of here is a manganese Mn plus 3 to Mn plus 2, then yes, this is what it is, standard reduction potential value is high, because again here is a Mn plus 2 has, here is a stable, yes, in Mn plus 3 state, Mn plus 3 is unstable, Mn plus manganese in plus 3 state it is unstable because it is having a D4 configuration. In plus 3 state it is having D4 configuration, that's why, yes, here again, yes, it gain the, here is what, it gain the, here is what, electron, and it is reduced. It is reduced because in plus 2 state it is getting D5 configuration, D5 configuration. So this is about, here is a standard reduction potential values. Yes, when standard reduction potential values are in positive sign, they act as, there is a oxidizing agents. When standard reduction potential values are in negative sign, then they act as, here is a good reducing agents. That means what, they can, yes, liberate the hydrogen gas from the aqueous acids. Okay, so this is the chemical reactivity of transition elements. This is enough.